In this video we learn about L'Hopital's rule. This is a really cool rule for taking limits, and I hope you will like it. It has to do with forming limits of rational functions, for example of the form limit xs goes to a, f of x divided by g of x. And then these are cases where we get 0 divided by 0 or infinity divided by infinity, which are not well-defined terms, and we have to make some sense of it. We will see later in a second video that the same method can be used for strange things like 0 times infinity or infinity minus infinity or some exponents which involve 0 and infinity. But let's first focus on the first two parts here, 0 divided by 0 and infinity divided by infinity. We take two functions f and g and we assume they are differentiable at a point a where g prime of x is not 0 near a. And as I said, we consider two cases. In case 1, as the limit x goes to a, f of x is 0, and the same for g. This would be the indeterminate type 0 divided by 0. And the other case is the indeterminate type infinity divided by infinity. Now here's the rule. So L'Hopital's rule that the limit of the ratio f divided by g is the same as the limit as x goes to a, f prime divided by g prime. Wow, this is really cool. Let's look at this again. So the limit as x goes to a, f divided by g is the same as the limit x goes to a, f prime divided by g prime. Wow, this is pretty cool, because this means if you cannot take the limit on the left with f and g, because it's 0 over 0, for example, you can differentiate the f and you can differentiate the g, look at the ratio and then take the limit. And you will see this is a very powerful method. And to indicate this limit properly, we use a little h here. So we write an h over the equality sign to indicate that we have been using L'Hopital's rule. Let's do two examples first, and then I explain why this should actually be true. Here we go. So evaluate the limit x goes to 0, e to the x minus 1 divided by x. F of x is e to the x minus 1, and if I take this limit, I get e to the 0 minus 1, and e to the 0 is 1, so this is 0. In the denominator, we have g of x is x, and limit x goes to 0 of x is of course 0, so then this has the type 0 over 0. This means we are in the business, we can apply L'Hopital's rule, so let's do that. Using L'Hopital's rule, we can write this to be equal with a little h on top, limit x goes to 0. So what do we have to do? We have to differentiate f. Maybe let's do that on the side here. F prime is equal to e to the x. G prime is equal to 1. Okay, differentiation now is easy. So we need to differentiate here. We get e to the x, and then we differentiate the g, which is 1. So we get this limit, e to the 0, which is 1. And we found a limit. Pretty cool, isn't it? Let's do another example. Here we have limit goes to infinity, log x divided by x. So if my function f is the natural logarithm, then the limit as x goes to infinity of ln x is certainly infinity. The function g is the same as before, but now we have the limit x goes to infinity of x, which is also infinity. So guess what the type is? Infinity over infinity. Again, this is a case where we can apply L'Hopital. L'Hopital equal limit x goes to infinity. We differentiate the logarithm, which is 1 over x, and we differentiate the x, which is 1. So then this is limit x to infinity, 1 over x, and this is 0, as we all know. Cool, right? Now let's look at this, why this is actually true. And I explained this on the type 0 divided by 0. I assume I have two general functions, which are 0 as x goes to a. If I plot this, I plot it like this. A coordinate system. And then I have a first function f, which is 0 at a point a. Okay, let's call this f of x. And this here is x. Let's do the second function, which is also 0 at a. What I now do is I go very close to a and express each of these functions by the tangent line. I use the tangent line approximation. Let's do this for f. I use the light green and I plot the tangent line at this point. So here, let's call this tangent line LF. And then I know that f at x is approximately equal f prime at the point a times x minus a. And then there would be a plus f of a, but f of a is 0, okay? So then this is the tangent line approximation close to a for the function f. Let's do that for the g function in orange. This is all right. So this is the tangent line LG. And then we have g of x is approximately equal g prime at a x minus a. And now we can study the limit. So then we have limit x goes to a of f of x divided by g of x. Now as x approaches a, we get close to a, which means we can use the tangent line approximations right here. So then this is equal limit x goes to a f prime at a times x minus a divided by g prime at a x minus a. And then we can cancel the common factor x minus a, and we keep the derivatives. So we keep f prime at a divided by g prime at a. So the ratio of the functions is the same as the ratio of the derivative in the case where f at a is 0 and g of a is 0. Pretty cool. So let me summarize. To study limits of the form 0 divided by 0 or infinity divided by infinity, we can simply differentiate the functions f and g separately and then look at this limit of the derivatives. That's L'Hopital's rule. Tolo, what's up? Tolo.